Hey everybody, welcome back. So in this episode we're going to be creating a swap chain. In the previous episode we made a surface. We have no way of sending images to that surface though. The swap chain is what's going to take care of that. It's actually a queue of images, and the application can request one of those images, write to it, and then return it to the queue. So as it iterates through there, it can take each one of those images in the queue and display them. And since you can write to an image while you're displaying an image, write to one while you're displaying another, you end up with a steady stream of images headed to the display, and that's what we want to have. So before we do anything, we need to actually verify that the swap chain is supported. So first off, since Vulkan doesn't actually have any window management code, we're going to need to use a device extension to actually handle swap chains. So first off, we're going to need to declare the extensions we're going to use. That's going to be over in the .h file. And if you remember, we have this set of validation layers right here. The extensions are handled very similarly, so I probably shouldn't copy and paste this. We'll do this by hand. It's probably safer. So once again, it's another constant std vector. Here we go. Constant char star. And we're just going to call this device extensions. There we go. And once again, we can use a nice little macro like this to get us the extensions we need. The one that we're going to need in this case is vk khr swap chain extension name. There we go. So that'll get us what we need to handle the swap chain extensions. So now that we have that, we actually need to check if the extensions that we're requesting are supported by the device that we're using. And since we need to make sure of that before we choose a device, we're going to need to call something within the rate device suitability function that we were using before. I'm going to drop it right down here. We'll just call this bool check device extension support. There we go. And once again, because we are checking a device, we need to pass in a device. So let's go ahead and just do a vk physical device, and we'll just call it device. There we go. So that'll give us everything we need. It's going to be called in rate device suitability, and it's going to actually end up being rather similar to the check validation layer support that we have up here. The structure is pretty similar. It's just going to iterate through and make sure that everything's there. Alright, and we want to, of course, create that in the CPP file as well, so we're just going to copy it over, and once again I'm going to drop it in roughly the same place. See if we can get it. Where'd you go? Yeah, we'll just search for it. It's much easier. Okay. Nope. There it is. I wanted to drop it right after find queue families because that's where it is in the .h file, and we might as well have everything match up. Oh, it was right at the bottom. That would have been simpler, wouldn't it? Alright, so we go ahead and put in check device extension support right here. And now that we have it, well, first off, let's give it the proper scope. Before we forget. Certainly don't want to mess that up. So now that we have it, let's go ahead and put that into our rate device suitability function. Here we go. And so we're going to want to place this right about here, right after the queue families. So if you remember, find queue families right here takes the device and checks what queue families are available to it, and it makes sure that there's one that meets our needs, and that's what it returns. So as long as it's filled out completely, then this indices.isComplete will be true, and it'll skip returning 0. We need to also check for the extensions. So it's actually going to be right after the queue families, but right before the check right here. We're just going to call bool extensions. There we go. Supported equals, and we're going to call check device extension support. And once again, we're going to pass in the device to rate. So we haven't filled it out yet, but in theory that will check to make sure that all the extensions we need are supported. It'll return true or false. And then if our extensions aren't supported, we can't use this device. So we're going to just say if not indices is complete, or if not extension supported. just like that. Because either one of those means that this device is useless to us. So there we go. Now let's go ahead and fill out that check device extension support. So we're going to drop right back down here. And like I said, the layout is really similar to the layers. So we're going to go ahead and just do a uint 32t extension count. And once again, we're encountering it again. Like I said in Vulkan, you have to call these enumerate functions twice. So we're going to do that just like before. vk enumerate device extension properties. Alright, and we're going to pass in the device, null pointer, the extension count, because we're going to override that, and then null pointer again, because we're not actually filling in any data yet. So that'll give us the number of extensions. Then, as always, we make a vector. And it's going to be a vk extension properties. Typed the wrong thing. There we go. And we'll just call this available extensions in caps lock. Alright, and then we're going to initialize that to extension count. Make sure it's the proper size. And I'm just going to copy and paste, because we're calling the same thing again, except this time we are passing in available extensions. There it is. And of course it's .data. So now we get all the extensions available to this device. We're storing them in that vector. And now comes the nice little nested for loop we used before. So we're going to iterate through all of the extensions that we requested. So, constant char star. I'm going to call it current extension, just so we know that that's the one we're currently looking at. And it's out of everything in device extensions, which is that constant vector we made in the .h file. Alright, and now we need to check whether or not the extension was found. So we just create the bool extension found, initialize it to false, and we're going to iterate through everything found in available extensions. So constant, just auto and, we'll just call it extension. That works. In available extensions. And it's, again, basically the exact same code, just if and string comp current extension and extension name equals 0. So once again, what that's doing is it's taking the current extension that we're retrieving from available extensions, and it's checking the extension name of it, and then up here in device extensions, everything stored was already extension name, so we don't need to call that. And we're just comparing the two strings. If they equal 0, it means that they are the same string, and we found it, so we can say extension found equals true, and then we can break. And then down here, if not extension found, so if it failed to find that particular one, we return false. Because as soon as we miss one, we know that this isn't going to work. And then down at the very bottom, we return true. If it makes it all the way through, we've got the extensions that we need. Now, if you remember when we made the logical device, there was a section to fill out extensions, and we never did that. So that's what we're going to do now. We have the create logical device, and right here we had enabled extension count 0 and extension name is null pointer, but we do have extensions now, so we can just call device extensions. The count is going to be size, it's the number that we requested, and the extension names are just going to be device extensions.data. So now we have all of that. So at this point, we have the extensions that we would need for the swap chain, assuming that there's any device on our system that can actually handle it, which there should be, I would hope. The problem is we don't necessarily know if the swap chain is compatible with the surface that we created. So we're going to have to check that. And again, I'm going to borrow some things from Alexander's tutorial here. As always, I encourage you to check it out. It's really fantastic. So just like back in the .h file, if you remember, we had this struct for the Q family indices that was storing a lot of the data that we would need. We're going to do something similar to that. We're going to make another struct, and this one's going to be called swap chain support details. There we are. All right, and this is going to store all of the settings that we would need for the swap chain. So we have three of them. There's VK surface capabilities, KHR. We'll call that capabilities. My spelling is so bad when I have all these papers around. Alright, and then we have two vectors. First one is going to be a vector of VK surface format, KHR. There it is. And we'll call that formats. And one more vector, and this one is going to be VK present mode KHR. We'll call that present modes. Alright, so that will store all of the data that we need. So now that we have a place to store all the data, we're going to need to have a function which actually fills out all that data. So what we're going to do is we're going to create a function called query swap chain support. That's going to be down here. Do it right after that bool from before. And it's going to, of course, return one of those structs. So swap chain support details, and then query swap chain support. And like so many other of these functions, we're going to pass in a VK physical device because it's going to check what the device supports. So we're going to grab that, bring it right back over to the CPP, and drop it in at the bottom. Right down here. Oh, nope, that's outside of the scope. The namespace, if you will. So, we have query swap chain support right here. And what it's going to do, it's going to start off by creating a new instance of the struct. We'll just call it details. And there's going to be a bunch of stuff, and at the end it's going to return details. Okay, so let's start filling that out. Oh, actually, I forgot one little thing here. Gotta add in the scope, or it's going to get very angry very quickly. Alright, so now that we have that, the first thing we need to get the capabilities variable. So just make a nice little note for myself. And the way we get the capabilities, we call VK get physical device surface capabilities KHR. There we go. We're going to pass in the device that we are currently querying, our surface, and then a reference to details.capabilities, because that's what we're going to be overriding. So that should take care of all the capabilities. Now we need the formats. Once again, this one's using a vector, so it's going to require that we call the same function twice to get the proper size and then to fill it out. This one's going to be slightly different than what we've encountered before, though, because it's not a new vector that we are declaring. It's a vector that already exists over here in the swap chain support details struct. So, first off, we need another size int, so we're going to make another uint32t. Call that format count. And then we're going to call vk get physical device surface formats KHR. And we're going to pass in device surface reference to format count so we can override it. And then null pointer because we're not filling out the information yet. And this is where we'd normally create the vector, and then call it again. Since we already have it, it's going to be a little different. We're just going to say if format count doesn't equal 0, then we know that it found some formats, and we can go ahead and resize the vector to be the size that we need it to be. So we're just going to say details dot formats dot resize to format count. So now that gives us the vector we need. Now we can call, I'm just going to copy and paste it, but call vk get physical device surface formats khr again. And this time we'll just go ahead and pass in details dot formats dot data. So that will override it with what we need. And finally, we need the present modes. So for this one, it's very similar. In fact, it's nearly identical. Uint 32t and present modes count that we call vk get physical device surface present modes. There we go. Surface present modes khr, and we pass in device surface reference to the present mode count and null pointer. I know this gets very tedious. There's not too much more to go through before we actually start rendering some things to the screen, so if people are getting impatient, I'm sorry, but this is all very important. Alright, so if present modes count does not equal 0, details dot present modes dot resize, not reserve, resize present modes count. I'm going to copy and paste this right in. Replace the last part with details present modes data. Alright. And then once again we return details, and that should be everything we need to get this running. So now that we have that, this will take any device that we pass to it, find out all of its information about what it can handle for swap chains, and store it in one of those nice little structs for us. So we can take that and we can use it to identify whether or not the device will meet our needs. We're not currently checking that yet though, so all we need to do is go back to rate device suitability, and we're going to need to add in some way of checking its swap chain support to make sure that it meets our needs. So this isn't really too hard. We're just going to make another bool, and we're just going to call this swap chain adequate. And we'll initialize it to false. And then we're just going to fill out a swap chain support details struct. And swap chain support. And we're going to fill that out using the function that we just created. So we're just going to use query swap chain support and pass in the device to rate. So what that's going to do is it's going to go ahead and call that, fill out a swap chain support details struct, and store it right here for us. And then we can use the data from that struct to identify whether or not the swap chain is adequate. So all we have to do is we set swap chain adequate equals, and we're just going to check if the vectors are empty or not, because if they're empty, it's not going to work. If they have some data in there, we know that they're okay. So we're just going to say swap chain support dot formats dot empty, and we're checking if it is not empty right there, and not swap chain support dot present modes dot empty. So it'll check, it'll make sure that both of those are not empty, and if they are not empty, it'll initialize this, it will set this to true, and if they are empty, it will set it to false. And then just like everything else, we need to make sure that everything's adequate. So we just say if not swap chain adequate, return 0. So if it goes through all this and it decides that the swap chain isn't supported, it returns a value of 0 for this device because the device is, once again, useless. So at this point, we have everything we need to make sure that our swap chain is suitable. The problem is there's still quite a bit that needs to be filled out to actually create the swap chain. So I'm actually not going to create it in this video. I'm going to do that in the next episode, but I am going to set up some helper functions that will help retrieve the settings that we need for certain things within the swap chain. So let's go ahead and start creating those. First off, we're going to need the swap chain's surface format. That's going to be one of its settings that we're going to need to fill out. That's stored in a VK surface format KHR structure. So we're going to go ahead and make one of those right down here, right underneath swap chain support details. So it's just a VK surface format KHR. There it is. And we're going to call this choose, I'll capitalize that, choose swap surface format. So this function is going to figure out which surface format we want and return that in the proper struct. So we want to pass in all of the available formats. So const std vector, and it's just going to be a vector of surface formats. There we go. And it's a reference to the vector. That way it can just access it directly and not have to copy anything over. Alright, now of course we need to go declare this in the CPP file again. Here we are. Before we forget, let's go ahead and put that scope. There it is. So the VK surface format has two variables to it. There's a format and a color space. Format contains the presentation capabilities, and then color space is just a flag. It indicates whether or not the engine can suspect sRGB nonlinear data. In case you're really curious about it, sRGB is just a standardized color format, and it functions better with the human eye. It doesn't follow a linear structure, but it means that the colors look better to us, so that's a pretty common standard to use. So first off, we're going to handle the format. So a lot of surfaces have a preferred format, and if it doesn't, then we already know what we want to set it to. There's some particular settings that would be ideal. So first off, I'm just going to make a comment. This is if the surface has no preferred format. So the way you know if a surface has a preferred format or not, you just check the available formats that are being sent in here. If the available format's size is 1, if it doesn't have a list of available formats, and that one bit of data, so we're just going to call available format 0 to get the first element, if the format is equal to VK format undefined, that means it doesn't care, it has no preferred format, and you can set it to whatever you like. So if that's the case, we're going to make this real simple. We're just going to return, and it's just going to be the data we need. So for the VK format, it's VK format, and we're going to say, it's kind of a long string of numbers here, but it's B8, G8, R8, A8, and then U norm. In case you couldn't tell, that's blue 8, green 8, red 8, alpha 8. And then for the color space, we're just going to go ahead and set the flag, which is VK color space sRGB nonlinear KHR. So that would be our ideal setting for the swap surface format. Now, let's say that there is a preferred format. If there is, then that means that we get to select the one that we want. So first off, we'd like to check if what we originally set right here is something that's available to us, because if it is, that's what we want. So we're going to iterate through everything available. We're going to say for constant auto and current format in available formats. So we're going to iterate through all the available formats, and on each one, current format is going to be the one that we are currently at. We're going to say if current format dot format equals, and we're just going to pull this in there, and if current format dot color space equals, and we're just going to grab this again because these are both kind of a pain to type out. So if we happen to run across the same two things that we want anyway, let's just return that. And now in the rare case that neither of these takes place, then we just need to return something that works. So we're going to go ahead and return available formats 0. Whatever the first thing available is, it'll still work, it just might not be ideal for what we're doing here. Next step, we need the present mode. So we're going to go back over here, and this one is going to be stored in a VK present mode KHR. And this is going to be another function we're just going to call choose swap present mode. There we are. And it's going to be very similar to what we did before. Just make another vector. And this is going to be of VK present mode KHRs. And we'll call it available present modes. There we are. Once again, copy it, drop it into the CPP file, add the scope, and add some brackets. Okay. Just went ahead and stopped the camera here so I could just type all this up. I didn't really want you to have to watch me typing at all. For the present modes, there's exactly 4 that you can choose from. There's present mode immediate, which means that the images are presented as soon as they're available. It gives you a high frame rate, but it can cause screen tearing. You have mailbox, where whenever a new image is being presented, it just holds it until the next vertical refresh of the screen. So the next time your screen updates, it'll present a new image. But if you get a new image sent before the refresh, then it'll replace the old one that was pending. So that one is a little more consistent. Then you have present mode FIFO, first in, first out. So the images are stored in a queue, and they're shown in order after each vertical refresh. And then you have FIFO relaxed, which is just like the regular one, with a slight combination of immediate. So it functions like a standard FIFO, except if the queue is empty when there's a vertical refresh, then the next image that comes up is displayed immediately. So this can also cause some screen tearing as well. In our case, what we really want to use is mailbox, because it's the best at preventing screen tearing. So what we're going to do is we're going to iterate through all of the modes available. So const auto reference current mode out of the available present modes, just like that. We're going to say if the current mode equals, and what we want is VK, actually I can just copy it from here, VK present mode mailbox KHR. So if we found that, we have exactly what we need. We can return it. And if it doesn't have that, the only thing that's actually guaranteed by the system is VK present mode FIFO KHR. That's the only one where no matter what, it has that option. The other 3 depend on the device that we're using. So we're going to go ahead and just at the bottom, if it doesn't return current mode, it'll return VK present mode FIFO KHR. And just drop that right in there. Alright, so we've got that now. We only need one more thing, which is going to be the extent setting. And this deals with the dimensions of the images that are being presented for the swap chain. So we're going to go back over here again. We're going to make another one. This is vk extent 2D. We'll call it choose swap extent. And once again, just pass in const vk surface capabilities khr and capabilities. So this is going to figure out which extent we want. So we're just grab that, back over to the CPP. Almost done here. Planet Vulkan scope. So right here we're going to choose the extent, which has to do with the resolution. Now normally Vulkan will actually set the proper values on its own. It'll match the resolution of the window that you're using. That's not always the case though. Some windows will allow you to choose your own resolution, and they have a way of indicating this. So in capabilities, we actually have a width and a height. It's capabilities current extent, and there's a width and a height. Now normally that'll just be what we need it to be. The interesting thing is if the width or the height is set to the maximum value of uint32, then that means that we're supposed to set the resolution to be what we want. So first off, we have to check whether or not it's the max. So we just say if capabilities current extent, and we're just going to check the width. If either the width or the height is at the maximum, they both are. So std numeric limits. We're going to check uint32t, and we're going to see if it's max. Oh, spelled it wrong. uint32t max. There we go. So if it comes up like that, we know that if this is not equal to the maximum, then it means that it's already given us the proper width and height, and we have what we need. So we're just going to return capabilities dot current extent. It's already given us something that we can use. If it doesn't, we need to identify what the best resolution would be given the window we have. So we're going to say else, and this is when things get a little bit tricky. Since we have to find an extent that will fit our window nicely, we're just going to go ahead and declare a new vk extent 2D actual extent. And we're going to set it to be equal to our window's width and our window's height. And I don't believe we have access to that yet. We have access to the window. There's window object. Yeah, we can't access the width or the height. So we're going to hop over here to window.h. And these dimensions that we had, we're going to move those up into public. I'm not sure that's where we want to keep them necessarily, and I may do some refactoring later to make everything prettier, but for now this will take care of what we need. So now we should be able to call window object, let's just retype this, window object dot window width. Let's see if it just kind of catches up. And then window object dot window height. Well, it's not complaining, so I think we're doing okay here. So that will give us the actual extent of our window. Now we need to set the width and height to the proper value, because this may not be exactly what we want. So we're going to go ahead and say actual extent dot width, and we're going to set it to the maximum value. So std max, not max align, std max. Ah, right. We can't use max because we need to include algorithm. Let's see if that did the trick. Yep, it's happy now. So we're going to need to check which one is the maximum value. So we're going to check between capabilities, min image extent, width. So whichever one is bigger, either the minimum image extent of the width of the minimum image extent of the capabilities, or the minimum value between these two, which is capabilities, max image extent, width, and the actual extent, width. So, better understand what's going on here. We're finding the maximum image extent and then the actual extent, which is the extent of our window. We're getting the width from both of those. And then we're figuring out which one is smaller. So if the actual extent of the window is smaller than the maximum image extent that we have, then we're going to pick the actual extent. Then we also get the minimum image extent, the width of it. And so we have these two values, and it's going to pick whichever one is the largest of the two. So it's getting the largest value within the range of what we can actually use. So that's what we're doing to find the width. The height is the same, except we're replacing anywhere it says width with height. So we're just going to go ahead and call that actual extent height, min image extent height, max image extent height, and you guessed it, actual extent height. Alright, so this will give us values that we can use effectively for our image extent. And then we're just going to go ahead and return the actual extent, because now we have changed the values to match whatever it is we need. Now that we have that, we can go ahead and run everything. That's pretty much all we need to do in this video. And it looks like we have an issue. Give me just one moment to fix this. So, as usual, it was something kind of stupid, and I should have caught this earlier. If we hop back over into planetvulkan.h, remember when we filled out the device extensions right at the beginning? Well, I did this wrong. This isn't supposed to be in quotes. This is supposed to be outside of quotes, and now it's much happier. It's recognized. This is something that's already built into Vulkan, so by putting it in quotes, it just confused it, and all the device extensions failed. So that should fix everything. Let's try running it one more time just to make sure everything is up to speed. Alright. And no errors. We are good. Everything is created successfully, and, well, I'm pretty happy with that, so I think we're good to go. Anyways, so that's all for this time. Thanks again for watching, guys. In the next video, we're actually going to make the real swap chain. This was just all the setup involved to make sure that everything worked okay. And once we have that up and running, we can actually get into, hopefully, some graphics. So, as always, thanks for watching. If you have any questions or comments, just go ahead and put them at the bottom of the video. And as always, if you'd like to be updated when a new video comes out, just go ahead and subscribe.